Hello, everyone. Good afternoon. We're here to talk about measuring Qt performance. I was expecting maybe a small crowd so that we would do some collaborative live coding, but I think we can still try it. Was anyone in this room in my earlier multi-threading presentation? No, some hands. So I can still make an introduction about myself for the other ones. So my name is João Abecasis. I come from Portugal. The name is very common there, and unfortunately, it has this tilde in the A that makes a sound that is not available in any or in many other languages. And so most people outside my country cannot pronounce it right. It will be okay if you just call me Joao and ignore that there's a squiggle there. I'm a software engineer at Nokia. I've been working in the Oslo office at Qt Development Frameworks. I've been there for the past 1.5 years. In Oslo, I'm part of the Earth domain. This is something we reorganized development recently around this domains: Earth, Air, Fire, Water. And I'm part of the Earth domain, where we work with file systems, I/O, networking, concurrency, containers, the object model, event loops. So in a way, we are the interface to the OS and the layer right on top of what the language offers. There, I'm the domain architect for the Earth domain, and I'm also heading a working group where we are trying to track the performance of Qt and try to identify performance regressions earlier. So the agenda for today is good news and bad news. We have very few slides, so we'll dive into code. So I'll just give a short introduction to performance, and then we'll write some benchmarks in Creator. Also, well, it all depends on how it goes according to time, but if we can, I have been playing lately with this a new algorithm for our ReadWrite locks. So what we will do here is come up with benchmarks for the ReadWrite lock and try to implement that new algorithm here and see what performance, what we can measure. So I had in my abstract that I would talk about what performance improvements we did for 4.7. So I'll just get that out of the way as fast as possible. What's fast in Qt 4.7? QML, of course, is very fast. Big focus there was to offer an API that could be supported in a performant way. There was a lot of work done on graphics, on our graphic systems, scrolling performance, zooming performance. That also ties into WebKit, which gained a lot from those improvements, and also it's where we got feedback also into what we could improve in the graphics, in our graphic system. The Alien widgets on Mac, it's a new widget implementation. It also allows us better performance. QStatic text allows us to do less, and so improve performance on anything that goes with text rendering. And we also got an updated JavaScript core engine that supports, well, the JavaScript engine in WebKit. It supports Qt script, and it supports QML, JavaScript in QML. So that's it to get it out of the way. So when we're talking about performance, well, even before I get to that, I should maybe turn that off. So performance what you want to do if you're concerned about performance, the first thing you should do is measure something. You should find a way to get numbers out of what is this performance? Sometimes we have a feeling that something is slow, but if we don't have numbers, we cannot really measure if it's slow or if we can improve or what can we improve. And if we can measure, then we can look at how can we do things differently. What can we make to speed things up? A lot of times, performance is about perception. I mean, in the UI, if you're compiling, there's little you can do to make the compile faster. Of course, you can get a better compiler. You can optimize it as crazy as much as you like. But when you're doing an IDE like Creator, we're not optimizing the compiles. We're just taking them out of the way, and then you get the feeling that everything is snappier and faster in the UI. So what kind of things can we do to improve performance? Once you start looking at, once you start getting numbers of measuring how long something is taking, then you can also start looking at what it is doing, and then you can consider doing things maybe sooner before it's needed, so that when you need something, it's done. An example of this is like code completion in Creator, where we parse your code before you actually need the completion, so that we can offer it when you need. You can do something later. For instance, in application startup, you want to delay. Your main focus is to get your application on the screen, to get the user to use the application. So anything you can remove there and do later at maybe when you actually need the stuff you were doing, maybe reading some images or configuration files. Do you really need to do everything there? This is something you can consider when you're trying to improve performance. Then you can look into doing things smarter, using better algorithms. Maybe you find out that your algorithms, the algorithms you're using for something has a really crappy performance complexity. And actually making things faster by just optimizing on the little lines of code is just one way of, it's most of the times maybe not the best approach. So besides doing all of this, of course, you can stop doing things. Like in QStatic text, one thing that this offers you is the ability to cache rendering of text into the screen. You cache the characters, the individual characters, and you reuse them so that you're not doing all the calculations there all the time. So you stop doing things. Maybe you find out you didn't even need them to begin with. So we're talking about measuring. Let's write a benchmark. Of course, I will be using Creator for this. And I just recently found out we have an awesome thing here, which is a cute unit test project. Before I was doing this by hand, that's how I planned this presentation. We can take that as is. Qt core. Yeah, we can write a small benchmark using Qt core. Of course, my class name cannot have a dash in it. I don't really need the version control right now. So this is what basic. This gives you the infrastructure for creating a basic benchmark. Or in this case, it gives you, well, test cases, unit tests. But to turn this unit test into a benchmark, I'll just leave that test case one there. I'll create a benchmark. I'll throw away the my. So what should we benchmark? Anyone has any ideas? No? Well, we'll benchmark a string creation or a string concatenation operation. So let's say I have to stop doing the my stuff. So we'll just say 100 times, we'll concatenate a couple of strings. I'll show you. Let's compile and run. Good. There we have. We run the test case, but we don't really have any, we don't get any measurements. So how do we turn when you have some code? Maybe this code is something you're going to put inside your benchmark because you extracted, you found out I'm having something weird happening here, so just gonna copy this code into a benchmark and try to optimize it from there. Or you could be calling a function that you have somewhere, so you wouldn't have to copy and paste the code. So the simplest thing you can do is wrap all that into a QBenchmark, the QBenchmarkLoop. And there you have it. All of a sudden, you start getting some results for your benchmark. So this is a very basic benchmark. What does QBenchmark offer you? You see here that we get this 0.058 milliseconds per iteration. It says a total of 30, and it says iterations 512. What does that mean? In QTestLib, in benchmarks, or the QBenchmark macro has the concept of a minimum value that it will accept, so that if you have something that is so fast that it's basically not measurable, it will iterate over it. Sometimes it will actually do a first round trying to figure out how many iterations it should do, and then it will actually do the benchmark run. In this case, it ran my loop. It ran this block for 512 times, and it got in the end a total of 30 milliseconds total, and that gave it 0.058 milliseconds per iteration. I'm actually going to change here the version, Qt version that I'm using. I just need to clean the project and rebuild it. Maybe make sure we run qmake. So now with Qt 4.7, well, I wouldn't trust there's a slight difference, 0.058 milliseconds to 0.056 milliseconds, but I wouldn't say that's a performance improvement from 4.6 to 4.7. It's too small a number to say. But one thing we did change in QTestLib is we increased the minimum number that we will accept, because at least for our benchmarks, the old number was 20 milliseconds, and that was showing us very unstable results going up and down. And by raising it to 50, then we do a little bit more work, but we get better numbers out of QTestLib. So there you have it, 1024 iterations, and then we get around 58 milliseconds for the total thing. So let's explore a little bit more of what QTestLib is giving us in this very basic and contrived benchmark. What was it called? Benchmark 1. So the same thing here, 56, 57, 58. That seems to be what we are getting out of it. But if you run -help, you get a couple of options there. And the ones that are interesting are the ones around here, benchmark-related options. So besides measuring, timing your code, one thing that we can do is, on Linux at least, oh, yes, I've hit this earlier. So call grind, we'll fix that. But call grind, the call grind option will do instruction counts, and that is supposed to be a better measure in some, depending on what you actually put inside QBenchmark. If it's code that doesn't change, that it always runs the same way, then an instruction count should be a very stable number that you get out of your benchmark. If your benchmark is going through the network, if it's doing a lot of allocations, then it might be more sensitive to to the state of the free lists in your application, or to the state of the network, timeouts and things like that. And then call grind might not help anything. But let's fix that. Let's make this a Q application test. Oh, actually, one thing we didn't do before is go over this. But has anyone here used QTestLib before? Not too many people. Yeah. So in QTestLib, QTestLib offers you ways to write unit tests, also benchmarking. Everything starts with a class that derives from QObject. So this is your boilerplate QObject derived class up to here. The constructor, I'm going to go ahead and delete that because we're not using it for anything. And you add some private Q slots, or private slots, and this will be your test cases. Each function is a test case that will be run. And whether this is a unit test or a QBench or a benchmark, then you decide. If you want, you can write your own main function, instantiate the object, and call QTextExec on your object. But this is the simplest of what you can get for when writing unit tests, and you get this for free from Creator. You just wrap your class name inside this macro QTestAppLessMain, and so we're going to fix this. So if your code actually depends on Q application and a GUI, then you would use QTestMain. And of course, since I have everything, my class and the code in the CPP file, then I have to include the generated mock file, so that it all gets compiled into one application. Need to add GUI as a dependency for my test case as well. Yep. Oh, everything is slower with Q application. So let's look what we get from call grind. So since it's doing instruction counts, it actually adds a lot of, uses vol grind, and it actually adds a lot of overhead to whatever you're measuring. So if you have something that took 5 minutes, then all of a sudden it will take a lot longer. Let's run it just twice to see what we have. In this case, my string concatenation is doing a lot of allocation, so I don't expect this to be the most stable benchmark, especially not if I'm doing a lot of other things at the same time. So this is one of the options you get. Let's look at the other ones. There's a tick counter, which I should have tested before coming here. I hope it works. It's basically also a timing thing, but instead of counting time milliseconds, we get tick counts from the OS. Events received during benchmarks, I'm not going to use that. I'm going to jump straight to the minimum value. If you find out that the 20 is good enough for you, 20 milliseconds for whatever your tests are doing, or if you really want to iterate it, you want the test to iterate for a full second or something else, then you can, wrong option, minimum value. Other options for getting different numbers from your benchmarks include actually specifying the number of iterations. This may be very important if you are comparing benchmarks doing the same thing, or two different benchmarks doing similar things, and you want to compare the results. Then if one is just doing one iteration and giving that result immediately, and another one is doing 1,000 iterations, and the errors in those numbers will be different. So you could want to you may want to control at the level of the number of iterations you're doing. Another option we have, and I'll actually use two now, is to ask the QTestLib to run your test cases multiple times and just give you the median of all those runs. And I'm going to add the verbose flag so that we get all the results per run of the benchmark. You will also notice there that the test case that I had before, or that creator offered me, is not being repeated. The only thing that gets repeated are actual benchmarks. And you get in the end the median here, 0.071 milliseconds. So once you have your benchmark, another thing you can do is run it through that's not what I wanted. Run it through a profiler so that you can actually analyze what's happening with your code and then try to improve it. So I'll just go into QCache grind and see the generated file from that. So all platforms have profiling tools. You should check your own developer, the developer offering on your platform, and just always measure, measure, measure. I can see Q applications taking a lot of my time on this. Yeah. Then you can go look into those things. You want to look at what the big blocks are. In this case, I'm also not sure that all we are seeing here comes from my benchmark. So when you're looking at the full picture, you should make sure that you're not looking at what Q application is actually doing. So I'm going to take that back out. Make this an appless main again. Compile it again. We'll just run it through call grind. I think we should get better results that way. Which one was that? So There you go, much better. Now you can actually do a lot with it. So then we see mem copy is taking up a lot of time in this code that I'm benchmarking and trying to optimize. And of course, you go look at the code, and it's obvious to everyone. Especially because I gave it away when I mistakenly started using the plus equals operator. If you're just concatenating strings and creating temporaries and then assigning that, then you are always copying all your data around. So let's stop copying and make just the smart thing to begin with and not prematurely pessimize our code. Let's try to run that again and see what the numbers tell us. So you see right there that I got performance improvement from 0.056 milliseconds. I suddenly go to 0.015 milliseconds. I get that almost for free. Even though this is a contrived and obvious case, you could tell it right away when I was typing, oh, why is he writing this code? The profilers and the profiling and measuring is what should actually be driving your performance improvements efforts. Because it's very easy to waste a lot of time trying to improve performance on something that doesn't affect your end goal. So let's just close that. Other things we could do here, just move stuff out of the loop. We don't need to be doing it all the time. Creating the concatenated string, you can just append to it. Oh, but this will give a very different result. And because all of a sudden, every time QBenchmarkLoop iterates, you will be appending to the same string. But I didn't plan this, but so when you write a benchmark, most of the times you won't have something that you just put everything inside QBenchmark and you get the numbers out for free. Sometimes you need to set up something before you run the benchmark, and even inside your QBenchmark, maybe if since QBenchmark will be iterating, you need to reset stuff at the beginning. So I could do here my concatenated string clear. That would be my cleanup. And at the end, it's good practice to always add some kind of validation that your benchmark is actually doing what you expect it to be doing. So I'm actually not going to use QVerify. QVerify just gives you a Boolean verification. QCompare allows you to compare two results with expected result. So if I'm doing 100 concatenations of 10 characters, that should give me something like 1,000 characters. And of course, you don't want your validation code to be anything that is, of course. You don't want your validation code to be something that is very expensive and that will completely shadow the code you're trying to measure. So sometimes simple checks, this is not a unit test, so you don't want a full validation, you don't want to compare the full string. You just want something there that gives you some validation that it actually performed the operation. So I have no idea if in the end, after I optimized my code, the concatenated string is what I expect it to be, but it is the size, so that's some validation. Unit tests should be checking that the code is actually doing what we want it to do, and the benchmarks should just be measuring. So this QCompare or QVerify that you put in the end will give you some assurance that something happened. Because one way I could optimize this code is just to comment it out. And then all of a sudden, It's so fast. Oh, and it passes. This is weird. Sorry? I didn't save the file. It should save it for me. Oh, there you go. A fail. Multiple fails even for each iteration of the benchmark. And this will give you a signal, hey, stop with your optimizing because you're actually, you're no longer optimizing, you're losing functionality. So if I didn't add that clear here, I mentioned that suddenly my test case was also not, well, I'll uncomment those 2 lines. If I don't add the clear there, suddenly my benchmark is, well, it will fail again because it's expecting that, I wrote it initially expecting that I get a concatenated string, a clean string to begin with, and I don't. And sometimes you will you'll be measuring code that you cannot just initialize in a loop because the initialization is so expensive that every time you do this initialization, what you're actually trying to measure disappears. So there's another macro for that, which is QBenchmarkOnce, which will only run your test case once, and we'll make sure not to run it in a loop. But it may run your function multiple times if you ask for, if you give it the median, or if you give it the median. If you ask for a median of multiple runs, it will still run the whole function multiple times, but the QBenchmarkLoop, in this case the QBenchmarkOnce, is no longer a loop, it's just a simple block. And there you have it. If my test case is so fast that the number I get is 0 milliseconds. So this is something you have to take into account when you're writing your own benchmarks. That you need to figure out ways to make it actually do something that is measurable inside the QBenchmark loops if you are measuring something as simple as string concatenation. Oh, why is it still running? So, now that we looked at the very basic benchmark, I said that we were going to actually try and improve our QReadWrite Lock with a new algorithm. So let's, I have some boilerplate prepared for that. So I'm just going to close this. And the boilerplate is actually code I'm working on, so that's why it's there. So I have multiple projects here. Don't worry about all of them. We'll be looking at just the test cases. And I have here a DevDays test case. It's a very simple test application like we saw before. So we want to measure performance of the ReadWrite Lock. So I'll start by adding that there. Oh, anyway, we'll get to that later. We'll also use QMutex just to compare the two. So, does everyone know what a QReadWrite Lock is? Show of hands. Who knows? Should I give a small introduction? So QReadWriteLock is a synchronization mechanism that allows you to have, when you're sharing data across threads, allows you to have multiple threads reading the same data at once, and at some point somebody will want to actually change that data, and then you that thread that wants to change that data acquires a write lock, waits for all the readers to finish, and then it's the only one having access to the object at that point. So the QReadWriteLock has the simple. Let me pull that up. So it has a very simple interface. You can lock it. Oh, you can actually read it from there. You can lock it for reads, you can lock it for writes, and you can unlock it. And we also have we also have some helper classes to actually help us to actually do the locking and unlocking for us. So what should we be testing? Can anyone offer a suggestion for a benchmark we could come up with for the ReadWrite Lock? No. The most basic is would be just. Sorry? If we want something that does nothing. Oh, no, that's not that. Then we'll just lock it in a loop and see what that gives us. I don't know what kind of validation we could do to the read locker because it does to the lock because it doesn't offer us a chance to query it if it's locked. Just assume that if you run, if you get past that point, the read is locked. So it's running the wrong application because I have multiple applications in this project. This really shouldn't be called interface. So just for comparison, I put the QMutex. Let's do the same thing for Mutex. Oh, I expected this to be slower. So as a comparison, we have there QMutex locker. The Mutex locker takes just 0.0010 milliseconds, while the other one takes 100 microseconds or something. Nano. And let's do the same for write locker. Sorry? Yeah, so the read-write lock is the same, it's common. You can either lock it for reading or lock it for writing. So this would be a basic, the most basic benchmark. What does it actually measure? We're locking and unlocking the lock in a loop. What does this give you? It's actually a very interesting use case because what it tells you is how fast you can, what is the overhead of locking the mutex when nobody else is waiting. So this is one benchmark you could be measuring. You could be interested in the performance of the lock when in an uncontested case. So for my new read-write lock algorithm, I have here just an empty class. We can start by having a lock for read. Maybe a lock for write. And I'm going to cheat a little bit because QReadWriteLock has a single unlock. And I'm actually going to do two different unlocking mechanisms. So the way QReadWriteLock currently works in Qt 4.7 is that it internally uses a QMutex, and it locks the mutex, it checks the conditions. Are there any readers? Does anyone hold the write lock currently? And then releases the mutex, and well, either it has acquired the lock and changed the state of the lock, or it hasn't and it wastes. So basically, every single operation for the read-write lock has to go through this mutex lock. So if you have a lot of threads trying to acquire the same lock either for reading or writing, even if nobody else is waiting, or no, if you have a lot of threads, they will be in a way serialized, at least even if they are all readers, while doing the lock for read. They will have to wait for the other one, for the previous one to finish the lock for read before they actually can check that they can also lock it for read. So I thought, why do we need to be locking a mutex? Why do we need to serialize the lock for read operation? And I thought, we have this as great atomic operations, QAtomicInt. So I'm just going to use that, a QAtomicInt. I should probably include it first. QAtomicInt. I'm going to use an atomic int for a reader count. What this gives me is that I can just read that number incremented in a single operation and become a reader if there are no pending writers. And the trick that I'm going to use here is that, well, how do I know that there are no waiting writers? What I will do is I'll set the reader count to a very big negative numbers when there is someone waiting. And so by doing a single operation, I will know that I can be a reader or not. So let's implement those functions. So my lock for read will just be a, what is the name of it? So I'm just going to make everything ordered. We're not going to go over memory ordering constraints here, this talk, and fetch and add 1, and I check if the result. So what fetch and add does is basically it gets the number, the current count in the atomic integer. It gets the current number and returns this number, but adds 1 to the value that's in memory. So if so when I said that I'm going to I said that I'm going to increment this number, and if the value that was there before was not negative, then I know that I can be a reader, and then I just return. So I'm not going to implement yet the rest of the code. So I'm just going to put, hey, if there's someone waiting, then let's break because this is not implemented. I'm also going to implement the unlocking, which will basically be the reverse operation. But in this case, I'll be adding -1, and I would assume that nobody is waiting if the number is still positive. So the last number that I can get is if I'm the single reader, I will go from 1 to 0, and in that case, the number that I get in return is 1. So if it's bigger than 0, there's no problem there. If it's less than or equals to 0, means this is a weird state. And so I'm just going to a Q assert there. As well. So let's use that. We don't need this for now. And this basically gives us some validation of it will tell us if we can get anything out of this, at least for the read locks, because that's what we are looking for. I mean, if there are no writers waiting, why should the readers wait for each other to finish with the locking to go ahead? And if we can do it in a single atomic operation, then all of a sudden all our readers can move can start reading all at the same time. So let me just add the include here. There was ReadWrite H. So in this case, we have no read locker. We'll just call the functions directly. So let's see. Oh. Yeah. Nobody saw this? Come on. You guys developers? Header file is wrong as well? I was Oh, I put the wrong one. Come on, guys, I was testing your attention. You obviously failed. So let's try that again. Oh, test finished unexpectedly. Yes? This is true. So you were paying attention. It's good that we have autotests. or in this case, asserts in the code. So what's the problem now? Or did it not compile it? So a QAtomic initialize is automatically initialized to 0. Yeah, I'm just answering your question. ReadWrite Lock, line 54. Yes, but I expected it never to get there. So when I add 1, I get 0. Yes, that's true. And then I decrement it, and lock for read, decrement.
That's greater than 0, greater equals 0, not less than.
Which one?
In the unlock. That returns 1.
If it It returns the state before. So it first gets the number. So it should return 1. Yeah, but so if it returns 1, it means it goes to 0. So actually, if it's less than 1, then something weird is happening. Either we unlocked and we didn't have the lock, or yeah, the return, I can add it here, but it doesn't change anything. It's a void function. Up. Sorry? Sorry?
Unlock read must be less than 0 because first we lock, we get 1, then we decrease 1, we get 0. 0 is less than 1, so it's true, and we come to the assert.
No, when we unlock, we first lock, and our counter goes from 0 to 1. And when we unlock, the counter goes from 1 to 0, but it returns 1. Yeah, so it returns 1. So 1 is not less than 1, so we're not going to assert when it returns 1. Yeah. I mean, just in case I'm wrong, we can add, we can explicitly reset this and see if that helps. Nope. So something went horribly wrong somewhere. Do I have the lock and unlock in the right order? Lock for read, unlock for read. ReadWrite Lock. Okay. Yeah? Okay, so it's not, yeah, then I'll just do a clean build because this is using static libraries, and maybe that's. It could be that it's not tracking. Yeah, so that was the problem. It wasn't tracking, well, among the other ones that we fixed. So the new read locker, all of a sudden, it's actually even faster than our Q Mutex. So well, this is the idea that I have for the next ReadWrite Lock. Of course, by then, when it actually gets into Qt, it will no longer be faster than QMutex, because a colleague of mine has improved QMutex to be just as fast as the ReadWrite Lock implementation that I'm working on. I was signaled that we don't have a lot of more time, so I'll just open the floor for questions. Here, in the front.
What tools do you use to investigate performance in the Symbian platform, in the Qt? Especially, maybe there is regression in the 4.7 and Qt 2.1. a lot of error related to this, about 10 errors.
So what do we use to investigate performance? We have.
How is it possible to? Because it's good to use Valgrind into the Linux, but which tools you use in the Symbian platform?
So to be honest, I will have to say I don't know because I haven't been doing a lot of Symbian development. But maybe later I can direct you to someone who actually knows, and you can ask them. Other questions? Yes,
how about benchmarking things with multiple threads then?
How so?
When you do like listings.
In this case, this was uncontended, and you're asking contended cases?
I don't understand.
I mean, if you're asking about measuring the performance of the ReadWrite Lock in a case where actually multiple threads are competing for it.
Right.
And so I have here another class that I'm using just for testing. Let me show the interface to it. So this inherits from QRunnable, which is something you can put into a thread pool just to run something in a thread pool. And the basic interface of QRunnable is that you override the run function, you implement the run function, and you put your code there. In this case, I'm creating a synchronized runnables, so that I can get multiple threads to get to the same point at the same time, and then I wait for all of them to finish. And I can. So this one has this virtual void synchronized run, which is what the code you are benchmarking would actually be implementing. And what this offers is that the run function actually is using a couple of semaphores to make sure that all the threads get to a point, and then all of them have left that point. And then what the benchmark looks like, I have a benchmark using this here. So I have a controller for that synchronizer class, and in the benchmark, I'm just running all the threads once through the loop. In my case, since this is just a test case for the synchronizer class itself, then each synchronized loop is just incrementing a counter. And I make sure that in this test case, I'm just making sure that all threads are counting the same number, so I've been run the same number of times. So that's one idea. Any more questions?
No, so thank you, Joao.
Thank you.